Hi, good morning, everyone. This is Nicole Testa Boston. I'm the Deputy Director at Tech, and I just wanted to welcome all of you and thank you for joining us this morning for a presentation on rapid on-site digital fabrication of sheet metal roof panels. Before I go ahead and get started and introduce Habib and William, I wanted to just let those of you who may be joining us for the first time using the GoToMeeting system that you are in a defaulted mute setting, so you're unable to speak to our presenters, but we do encourage any comments, questions, or points of clarification that you'd like to make. You can do that by using the Questions tab on that toolbar that's in front of you. Those questions and those comments will go directly to me, and then we'll take the last 15 minutes or so of this hour, and I will moderate a Q&A with the presenters based on the questions and comments that come into me. So please do feel free to use that at any time during the presentation, and we'll get those questions answered at the end of the session. We also are recording this session, and we will be making a copy of it available at the fabrication.org website. So you will be able to get a copy and share it with your colleagues. And last but not least, the toolbar is unique to you. So if you click that orange arrow up at the top, you can minimize it and have an unobstructed view of the presentation and get that off of your screen. So with that, I want to go ahead and thank Habib and William very much for joining us today to present this work. Habib Fatih holds a Bachelor of Science degree in Civil Engineering from Iran University of Science and Technology. He's got a master's in construction engineering and management also from IUST, and is currently a PhD student at the Georgia Institute of Technology. He's been working as a graduate research assistant at Georgia Tech since 2009, and during his doctoral study, he has worked on 2 videogrammatic research topics, 3D point cloud generation of civil infrastructure, and a 3D wire diagram generation for as-built documentation of civil infrastructure. Thus far, his efforts on these topics have led to 2 provisional patents and several journal and conference papers. He's joined today by William Wilkins, who is the COO of Metalforming. He was formerly a lieutenant commander on U.S. nuclear submarines. He holds a BSEE from Auburn University and MSCS with a concentration on networking from the Naval Postgraduate School in Monterey, California. Mr. Wilkins led the software development of the OnLink TM service system in collaboration with Microsoft, Level 3 Communications, and CIRM broker manufacturing software with Georgia Tech. And he has started and developed a new software development business at Metalforming and is responsible for running operations at the company. So with that, I want to go ahead and turn it over to Habib, who will be doing the start of the presentation, and then switching over to William midway. So thank you very much.
Okay, good morning everyone. Hope you are having a great day. This is Habib Fatih, PhD candidate from Georgia Tech, and today I'm going to present a framework for rapid on-site digital fabrication of sheet metal roof panels. This presentation will have 2 parts. The first part is the videogrammetric measurement section, which I will be the presenter. And the second part, which is the digital fabrication of the sheet metal panels. For that part, Mr. Wilkins will be the presenter. In general, as you know, in the construction industry, a structure has always tolerance errors, and it is never built to the exact drawing dimensions. Every subcontractor must do a measurement for the work that the previous subcontractor has done in order to be able to do the work that he is supposed to do in the project. However, in the sheet metal roofing industry, in specific case, a contractor must measure a roof for several times during the course of its build. One of these measurements is to measure the as-built dimensions of the roof after installing the underlayment. The measurement in this case is usually in the form of end-to-end dimensions of the roof plane boundaries. These measurements, when acquired, are then need to be presented in an XML file format in order to be readable with machinery that is used for digital fabrication of sheet metal roof panels. So once those measurements are acquired and uploaded to the machine, those machines can roll, form, and cut metal coil into panels ready for final installation. You can see the process in the bottom of this slide. So we do the measurement, then the measurements goes to the machinery for digital fabrication, and then the panels are overlaid on top of the roof. There are several measurement methods currently available in this industry that can be used in different steps of a roofing project. The first method is a very simple tape measurement method. In this method, a team of roofing employees go all over the roof with a tape measure and take the measurements manually. Hence, it's a very simple method and requires minimal expertise. But the problem is that it creates safety hazards and also is labor intensive. As a statistic, just 7% of private construction fatalities in 2009 was in the roofing industry. So we can see the importance of this kind of hazard in this industry. The second measurement type is using a total station and a surveying crew. This measurement system is safe and also accurate. It's accurate such that it sometimes it's more accurate than what we need in the industry. But the problem is that it needs a crew from trained surveyors, so it needs expertise in the process. Another measurement process is using aerial photogrammetry. There are couple of companies right now in the industry that does this kind of measurements. So the process is that you just enter the address of your project or the roof structure that you want to measure in their website, and then they pull off some aerial photos, and then they do the measurement process from that automatically. But this process is very inexpensive. It's simple for the customer, and there is no requirement for on-site labor in order to do the measurement. But the main problem is that it's kind of inaccurate, especially for fabrication level accuracy. Errors can be up to 5 inches or plus or minus 15 centimeters in this method. And also another type of measurement system that can be used is laser scanning, but it is not really an option because it is very costly, and not everybody can afford that to use that for the measurement process. For the kind of measurement accuracy that we want to deal for digital fabrication of sheet metals, we need kind of fabrication level accuracy. By fabrication level accuracy, we mean errors less than plus or minus at most 2 centimeters. For that kind of accuracy, from those measurement methods that I presented, only 2 of them can be applied. The first one is tape measuring, and you can see that in terms of cost, it's kind of inexpensive. The accuracy can be provided, it's simple to use, and it's efficient. But the main problem is the safety of this process. Another method was total station surveying. In terms of cost, it's a little bit more expensive than the tape measuring, but it is accurate and it is safe. But again, the main problem is the expertise that is required on the job site, and not all roofing contractors can afford that. So according to these parameters that we assessed, tape measuring is still the standard practice in the industry, and almost all of the roofing contractors are using this method in order to get the measurements. So we can see how, very simple methods are being used, and this is kind of inefficient in terms of cost, in terms of time. So what can be an ideal solution for this case? An ideal solution is inexpensive, is accurate enough for fabrication level. It's simple to use, no expertise is required, and it is safe, and it is also efficient. By efficient, we mean that it's kind of an automatic process, so it is efficient in terms of time and in terms of cost for the labor or the equipment. So if you consider these parameters for an ideal solution, a machine vision based algorithm or method which uses kind of videos or digital imagery in order to extract measurements has some of these ideal parameters already. It is inexpensive, it is simple, and it is safe. But what is remaining to consider is first of all the accuracy of these methods, and second of all the efficiency. So a general machine vision based approach cannot provide that fabrication level accuracy. But if you provide a method that is specialized for roof structures, there is a very high chance in order to be able to provide that accuracy. And also, if we can make the entire process automated, we can also satisfy the efficiency parameter. So I will start to present a little bit basic concepts about machine vision based surveying, and then I'll present the method that we have developed. So in general, machine vision based surveying works based on this rule that a 3D shape of a structure is generated or perceived first of all by analyzing the local motion of a camera set. You can see the process at the bottom of this slide. So if we have a static structure like the red points that you can see there, so we can kind of acquire the 3D shape of this structure by having a camera moving around this structure. So while the structure is static, the camera moves in the environment. And the way that it works is that it has two main steps. First of all, you have to find corresponding image features in different views of the scene, as you can see in the bottom. Those 2 points are the same points in the structure that are viewed in different images. And then when we have those corresponding image features, we can just use a simple triangulation method in order to get the 3D coordinates of those points. In the recent years, there are many new algorithms that have been developed and actually increase the efficiency and the accuracy of the method. So based on those algorithms, right now we can achieve centimeter level accuracy with just general machine vision based algorithms. But the point is that most of those algorithms are point-based methods. So the way that they work is that they look for very distinguished points in the structure and try to match them in different views and then extract the 3D information. So the limitation for that kind of algorithm is that, first of all, they only work in highly featured environments. So if you have a very poorly textured scene like a concrete wall or an aluminum membrane, these methods usually fail in those environments. And second of all, there is no guarantee to be able to reconstruct desired points, because the desired points are not guaranteed to be feature points. And hence, these two limitations exist for only point-based kind of 3D reconstruction methods. But nowadays, there are many researchers that are considering the combination of points, which I mentioned, and also lines. Lines are another kind of visual features that can be found in different views from man-made environments. Usually man-made environments consist lots of line features, and the point is that usually contractors are interested to get the measurements for those lines. So if we somehow can be able to combine points and lines together and provide a method that does that, it will enhance the accuracy and provide the requirements that we need in the construction industry. So our findings so far in this process for measuring roof structures are kind of the following. First of all, the roof structures can be geometric modeled as an ensemble of planar surfaces. These planar surfaces are usually a polygonal faces. So in a roof structure, we are dealing with a number of elements, and each of those elements is a plane. The next point is that the interesting parts to measure in a roofing project is boundaries of roof planes. We are not interested in anything else, just the boundaries of roof planes, and that is sufficient for any kind of post-processing or digital fabrication that we want to do. But in terms of the videogrammetry or photogrammetry and getting measurements from images, there are 2 points. First of all, the factors that are affecting the accuracy of this process is the calibration of the camera, which is a process that is done kind of manually. So if we do that with very high accuracy, we can expect better accuracy in the results. And also the feature detection and matching step. So if we can detect these features robustly and be able to match them robustly in different views, we can generate 3D information. Otherwise, there is no way to be able to do that. Also, the second point is that errors in this kind of measurements from videos or imagery can be usually reduced using higher level visual features. I mentioned that most of the methods are using point level information, but if you can somehow combine information from points, lines, and preferably planes together, you're using higher level visual features, and it helps to increase the accuracy of the results. So based on these findings and that overview, here is an overview of the approach that we are presenting. It has kind of 3 steps. The first step is stereo videotaping at the job site. You can see we have a stereo camera set up there. So the roofing employee can simply take this video stereo camera setup, record a stereo video from the roof, and then send that stereo video file to the processing step, data processing step, which can happen in a server or in a standalone version of the software. What happens in the data processing step is that, first of all, the method finds 3D lines from the scene, and after that, by finding different roof planes in the scene, it extracts the measurements from those 3D lines. Then those as-built measurements are converted to an XML file format, and they are sent to the job site for panel fabrication. On the job site, a cutting and folding machine can be used, and this information can be uploaded to that machine, and then it automatically roll forms and cuts metal coil into panels ready for final installation, which you can see an example at the end. So in order to kind of prove the concept for this project, we performed several case studies, but this is one of them that I'm presenting here. So we did a set of experiments on one side of a simple roof structure, which you can see on the upper right corner of the slide. The camera system that we used was a stereo camera setup from 2 Philly 2 cameras, which are very sensitive computer vision cameras. You can see them on the lower right corner of the slide. The baseline distance for the cameras, which is the distance between left and right camera, was almost 27 centimeters, and the resolution of the video was 5 megapixels. And the frame rate for the video was kind of averagely 7.5 frames per second. In the data collection process for that, if I want to start from the left side, we first of all, we collected data from the ground using the extendable pole that you can see there. So the cameras are on top, and we used an extendable pole and using a person to hold it, and then we just walked around the roof structure. In another experiment, we used a lift in order to take us to some higher elevations in order to kind of have a top-down view to the roof structure, and we also collected data using that method. Also, as a ground truth data for measurements, we use total station in order to get the measurements, and we also had the kind of measurements from manual measuring system using tape measurements. So in the processing step, we started from line segment detection, which you can see in the middle column. Those lines were then used in order to generate 3D lines, and from those 3D lines we could extract the roof planes available in the scene. Then from that we could extract some sample measurements that you can see here in terms of centimeters and just the boundaries of the roof planes that we are interested in. As I mentioned, total station measurements were used for ground truth data, and the result was that the 95% percentile error of the measurements were almost plus or minus 1.6 centimeters, which is kind of a little bit more than a half an inch. And these data were collected from a distance of approximately 15 meters from the object. So I have a kind of a video that can show more details about this case study. You can see setting up the hardware system here, the method that were used to collect data from the ground. We worked around the roof structure with the extendable pole, and here is the kind of captured data: stereo video, left view, and right view of the structure. So as I mentioned, the main step in the processing was to detect lines and combine that with points. This is the line detection step, and then those line segments are converted into 3D. And from that 3D data, we could extract only the line segments that are at plane boundaries, which you can see an example here. Then from those boundaries, we could detect the available roof planes in the scene. And from the planes, you can simply extract the measurements that are required for digital fabrication. And finally, presenting the output in an XML format that is directly readable by roll forming and cutting machines on the job site. But this kind of measurement method is a general measurement method, that it is not restricted to roof applications. For example, I have another application for this method for facade measurements here. In the top row, you can see the kind of data collection process. It was a facade structure in Georgia Tech campus with aluminum membrane, which is a very poorly textured scene. If you want to use just the point methods here, they would definitely fail. But the trick for us was to use points and lines in the combining together, and from that we could generate these sample measurements that can be used for documentation or even fabrication of those aluminum membranes. Here you can see some examples. But if I want to conclude my presentation from the video with gravimetric surveying part, I can say that the fast and non-contact measurement method that we presented for roof structures is kind of a significant upgrade compared to the existing measuring methods, especially the tape measurement method, which is the standard practice in the industry, both in terms of safety and cost. It is a very safe practice for employees, no safety hazards for them, and it's also very cost effective because most of the cost is in terms of software, and there is a little bit cost involved in terms of the hardware. The point was that general 3D reconstruction methods from photos or videos can be used usually for well-textured scenes, and they can generate good results with centimeter level accuracy for them, but these errors could be very high for non-textured environments that we are dealing with, and hence it is not good for fabrication that we are interested in. So the proposed approach in this presentation reduces the error to acceptable level, but combining higher level visual features in addition to points like lines and planes. And as future steps, it needs to be more tested for more complex structures in order to completely prove and validate the usability of this method in different kind of structures that we may deal. So this way I conclude my presentation, and we'll switch to Mr. Wilkins in order to present the digital fabrication of roof panels.
Okay.
Yep.
Let's see. I think, Nicole, you'll switch it over to me.
I will. Thank you.
Thank you.
Great.
Can you see it? All right.
Yep, we're all set. Thanks.
Okay. All right. Well, thanks, Habib. Appreciate that. Great presentation. And I welcome everybody to this webinar. My name is Bill Wilkins, COO here at Metalforming. Metalforming is a company who's been around for about 13 years, and we've basically sold all types of fabrication machines in the metal component market for roofing and such not. We also have sold through North America. We work a lot with customers up in Canada and U.S. and so forth. I just wanted to go through and kind of expound on what Habib has talked about, add a little meat from a business perspective, kind of put it together as a story and show you how important this technology is to us and to our customer base. Back in 2010, we approached the team at Georgia Tech in the civil engineering area at Georgia Tech, looking for a solution that could marry to our fabrication machine, specifically a Quadro Cinco machine that actually makes standing seam panels for a roof. We were looking for a solution that provided accuracy in order to drive this machine, and we've looked at several different types of products like total stations. Actually did some design work to see if we could make that work. We also worked through some laser scanner solutions, and for different reasons kind of identified from Habib's presentation, they just were not working for us. When we approached the team, we saw that the videogrammetry department at Georgia Tech was working on a technology that was basically using videogrammetry on bridges. And we're like, why can't we apply the same technologies for the different areas in our market? It sounded like a good idea. At that point, we started working with that team, and a year and a half later or so, here's where we stand. Okay, so one of the things that we were trying to solve in our solution, and I got 3 slides here that I'll just touch on and get this open for questions and stuff. But we had 2 main areas that we were trying to focus on. One was fabrication in the field, and then the other was fabrication in the factory. What I wanted to go through and show you a little bit about the process of what roofers are trying to solve as they estimate and they go through and they make panels for these roofs out in the marketplace. And just to give you a feel for how big the market is, there's over 19,000 roofers in the U.S. and about 13% of that market is in the metal market particularly. And this process happens, this measurement process happens on these roofs about 3 to 4 times during this process that I'll walk you through. Okay. The process starts really with an architectural drawing, and this drawing basically is a blueprint that creates an estimation of what kind of panels they need to make. Well, that estimation that we call as drawn is never the same as the as-built dimensions when the actual roof goes up. There's a lot of things that contribute to that inaccuracy. You could think about some types of warping. You can think about the steel bolts in the cement not setting properly that cause some skewing errors and basically unlevelness. But it happens every day, and you can kind of see it in this diagram at the bottom here. You see differences in measurements on the left side and the right side. Okay, so it's important that they go up and get those as-built dimensions so they can compare to drawn, and then they can fabricate the panels the way that they need to. The first step we took into solving that was to create a machine that could be used in the field, okay? A portable generator-based machine called the Cinco, and it could go out into the field and basically cut up the panels as the measurements were coming down from the tape measure, okay? So, like I said, the second step is estimation, okay? There's estimated pieces of trim and roll form panels would go out to the job site. And the traditional way, like Khabib said, was tape measure, okay? And tape measure in itself is a very risky process. First of all, from a safety standpoint, as you know, all types of roofings have different slopes, as you can see in the bottom left here. This type of roofing where this guy's on the roof, you can see if he slips and falls, it's not going to be good for him. Some roofs are very inaccessible based on the slope itself. It's an inherently dangerous process. There's rules coming out from OSHA that limit and basically complicate a roofer's job as far as them going up and measuring, having to have harnesses and stuff like that, which slow the process down. Of course, it's the best benefit of the person working there for safety reasons, but ultimately you're trying to put up roofs as fast and as efficiently as possible. Also, other things that contribute to cost for our customers is insurance and so forth like that, in order to insure these guys when they do fall. And like Khabib said, the 7% of fatalities, we like to get that down to 0. Okay, and also tape measure has tendency to be time consuming. We've done some studies to look at how long it would actually take to go through and tape measure and what the time savings would be if they use video serve versus a tape measure. Some studies we looked at, 30,000 square foot cut up roof normally take about 6 hours to do with a tape measure and about 2.5 hours to transfer all the data over. And as you can imagine, there could be a lot of mistakes there. Those mistakes translate to fabricating wrong products and then slow the whole process down to trying to get the roof up. We looked at, essentially doing it with video serve and reduced that down to hour and a half, about 13 hours worth of savings per roof. And they normally, like I said, do this 3 to 4 times through this process. Okay, so after the video serve piece is done, typically in the machine, like Khabib had said, we provide it in a format that could be downloaded to a machine. We think the Cinco is a good starting platform because it generates essentially these planes here and actually cut the angles. So we start talking about, instead of generation of panels, we start talking about generation of planes, and people can look at that as, let's make plane 1, let's make plane 2, and so forth. Okay, so once you're able to get real as-built dimensions, then you can actually fabricate those in the field. And what I'll talk about later, which we were trying to solve, is the ability to bring that same machine into a factory and produce a plane like a piece of a puzzle that could be shipped out to the roof and actually installed correctly so it fits. Okay, so that's the process: loading it, forming it. You can see this angle cutter here, actually one piece of this plane like right here, and then at that point we install it. So that's what we're trying to solve here, and this is what we call the Cinco, computer integrated notching cutting operation. Okay, so that was the first thing we were trying to solve. The other piece of this was, how do we get this same type of accuracy, type of wireframes with these dimensions to a factory? Some of the things we've been working on several years is the ability to provide a solutions platform called Computer Integrated Roof Manufacturing, CERM broker we call it, an ability to tie in ERP systems, the ability to tie in sales order entry systems to the process of fabrication of the machines, because it's not always roll forming, it's not always cutting. We have shearing operations. There's folders like down here that actually create different trim pieces and so forth. And the system essentially manages the manufacturing flow, even to the point where we're shipping the machine, the products out to the customer. The only piece missing from this is the as-built dimensions. And of course, if you want to measure and record all the tape measurements and do this 4 times and take this back to the factory and not having a chance to verify, you're kind of setting things up for potential error there. The other interesting thing too that the current way that our market actually makes these roofs is they actually make a parallel panel. And the parallel panel, if you go back to this slide here, they will actually produce a parallel standing seam panel, and they actually have to go up to the roof. And this is not tape measure. This is actually to make it fit on the roof. They have to go up here and make a longer panel that comes up to this point. Then they have to use cutting snips to go through and cut this piece here. You can imagine that takes a lot of time, and it's also very hazardous because you got metal there. You got to use gloves. If you don't, then you potentially cut your hand and you're bleeding, so forth and so on. So the Cinco first step was to solve that issue, where you could actually make the plane and get away from actually having to cut it with snips. So back to the factory solution. Essentially, having these as-built 3D dimensions, of course, you can take these and make two-dimensional diagrams out of those. You can actually provide the input to different types of machines. We also in the factory can take the different pieces and parts and optimize those with a thing called CERM Nest, which allows to minimize the amount of scrap of metal that you actually make during the process, which is a very big cost factor for customers. So it's the integration from a calibrated sensor back to the factory. And then once that happens, then essentially our customers, their second set of customers, not the roofers, they're metal component guys that sell these products, can actually make a plane, do some custom work, if you will, for the different roofers out there, because that's the products they normally sell to. So they sell a plane that's already cut up, it's packaged up, it's ready to go on the roof. Okay, no remeasurements, no nothing. It fits like a puzzle. So those are a couple of the things I wanted to talk to from this flow, and it's from a business perspective. Some of the things we've looked at as far as getting the ability for our customers to use this in a low-cost manner is this cloud server concept. One of the things that we've realized in our industry that some of the other companies are doing more on the estimation side, just providing estimation stuff because they're using aerial photography and they're using satellite imagery, is basically to go through and one other point I wanted to mention about this company that deploys these solutions is that they cannot address all the different markets in the roofing industry. There's re-roofing, there's also new building construction. So not only these companies can only address estimation, they can really only address re-roofing because most of the database that they have access to is ArcGIS photos, ArcGIS, and those are basically for re-roofing scenarios. But we do see a new construction market that's pretty big. But the question is how do we get that to a low-cost method to our customers? And we've looked at essentially a process where customers could go through and use a video camera. And right now this video camera is a stereo camera to provide extra accuracy, and they could videotape. And we saw that this is a big advantage because most everybody has done some type of videotaping before, versus our older technique that we were trying using a total station in the surveying. We just see that our roofing customers just don't understand surveying, nor do they want to. So the video concept is really an easy and neat concept. But once that video is captured, they would send this back to the server would process it, and it would come back with a 3D wireframe with the dimensions, the square inches, square foot, and anything that the customer would need to provide that as-built map for all these different products, as well as being able to take it to the next step, which is integration to the factory, communication to the machine, so it can understand what it needs to make and fabricate, and so forth. So some of the processes, video serve, you go through and order it, send it, optimize it, some of the things I've already talked about, fabricate it, and load it and send it. So some of the different parts of fabrication that this technology could use is a slitting and cutting process, the shearing, of course roll forming and angled cutting, and some of the trim parts, all the different pieces and parts that make up a roof. And we did see that the technology fit very well with the roof, and that's why we picked this industry first. One of the things that the technology that's growing from this in our partnership with Georgia Tech is the ability of using points and then creation of lines and then creation of planes, which are the intersection of lines. The technology eventually will progress, but as of right now, it's not designed to provide that level of accuracy for like irregular shapes. Okay, it's very good at doing lines and planes and so forth. And of course, a roof, that's what that's all about. Eventually, circles, different other types of shapes and so forth will be coming into the mix here, as long as there's equations behind that structure we're using. We've also looked at not only architectural roofs, we've looked at the flat roofing market and some of the membranes that they have to create. These membranes are basically cut out, pieces of membrane that have to get cut out and then laid out on the roof. This technology could apply there. So we see a lot of applications of fabrication throughout the building envelope out in the construction industry. So some of the different pieces and parts that we're talking about here, just to kind of expound on your understanding of the fabrication process. This piece over here, we work with a company called TopView, and it handles a lot of the estimation from the building of the entire roof down to the pieces and parts. And then the Quadro, essentially, using some software on here, could drive the creation of the planes and the setting of the angles and the cutting of the panels and the notching that has to occur prior to the metal going in. So these are, I've always designed to work together. Now the piece of bringing in, this as drawn technology here, and then be able to put in as built in here, and also drive this controller on this the CNC controller on this Quadro machine is what we're shooting for next. But it's not just limited to this machine. We're looking to adopt this process to an open data standard for BIM, building information modeling, and using some of the IFC to XML formats. We're also looking at other formats that could be used by the customer, like DWG and AutoCAD files and so forth. So we're not looking to limit the technology to a certain proprietary standard. We want to keep it open so people can use it. We also want to build this potential cloud server that could provide points and lines upon request. So if some more technical savvy customers want to build their own applications behind that, we could provide some of the software development kits to do that. To ultimately supply what they need. So in wrap up, essentially I wanted to give you a kind of feel for some of the solutions that we're trying to apply this to. But the technology, we realize it even goes beyond fabrication. It can go out into more of the estimation market. It can also go into fabrication indoors. In fact, this technology is very accurate indoors. It is a little more challenging outside because of all the different conditions and lighting, and it's also a little longer range. But we feel the combination of using videogrammetry with motion and the creation of lines, ordered points and so forth will provide the solution. Still got a little ways to go, but we're very confident and it'll work, and can't wait to get the solution out there. So that's all I got. I'll turn it back over.
Thank you. Thank you. Thank you both. We do have a question here, and for those of you who maybe joined late, you can use your questions tab on your toolbar there. Those questions will go directly to me, and I can forward those on to Habib and William for the time that remains here. One person asks, is there an optimum distance range of holding the video cameras to capture the exposed structures in order to get accurate featured points and lines and to generate 3D models?
Actually, the distance is one of the most important factors in terms of the accuracy of the final result, but that is not the only one. There are other factors like the resolution of the camera, the baseline distance between the left and right camera, and also the distance between the camera and the object. So the combination of these three should be kind of optimum, and it can be kind of different for different structures that we may deal. So in summary, I can say the optimum distance based on our experiments is kind of something between 10 to 20 meters away from the structure when we are using a 5 megapixel camera, and the baseline distance is kind of 30 centimeters. But if this combination changes, then we need to kind of reassess the optimum distance.
Okay, thank you. A question about just, I guess, other applications. I mean, this one here, and I should have mentioned in the opening, Georgia Tech and Metalforming were awarded a SETI award by the FIATech SETI jury back in March when we met in Florida. So one of the things we've been doing in these Technology Tuesday webinars is featuring those award winners and providing more details on the technology and applications that received the award. And this was one of the award winners in the intelligent and automated construction job site area. I know the jury, when they looked at this too, they discussed, and maybe you could address a little bit, other applications where this technology could be used and where you could see it applied in our industry.
So,
okay.
Yeah, Bill, go for it.
Okay, yeah, so a lot of different areas that we can see it being used. Basically, you know, one of the things we looked at is indoor applications. For instance, think about when you're remodeling your kitchen. You know, for the most part, if you're doing it yourself, you want to get your quick measurements, and you want to get out the door, get to Home Depot, so you can get the pieces and parts that match. So the application would be, say, modeled for more of a consumer market, where they could maybe put it on an iPhone, use one camera, okay, and basically take a quick video, and by the time that they're to the store, you know, they have the different measurements. A lot of different industries, talking to different customers down at FIATech, you know, the use of some of the point cloud generation, where you can use video and generation of a point cloud in a, you know, a cheaper, more automated fashion, you know, basically to estimate progress on a job site, okay, where you could easily use built-in video cameras that are already in play, and you know, they're already taking video streams, you know, where you take that and you run it through this processor where it creates you know, dimensions and so forth, that, or basically give you a visual snapshot with point clouds and so forth, just to see, well, is that pipe been installed, or is it, you know, where do they stand in this? So you could build on, you know, intelligent applications that could read the status of those point clouds and basically generate automatic status reports. You know, even in the building envelope market, we see a lot of different things: wall panels, ACM panels. One of the pictures that Habib showed you is generation of those. So a lot of the things of, you know, anything in the area of fabrication we're really focusing on, but it goes beyond that. It goes, you know, into industries where they want to use it in other applications. And we know we're not going to figure it all out. You know, part of the process of providing a server and software development kits is the ability, and an open standard, is the ability for people out there to use it in their ways. Okay, integrate with you know, Google SketchUp, integrate with a couple companies we've talked to that do a very good job of rendering as built and as drawn 3D wireframes on a roof. You know, so there's a lot of different applications we brainstorm. In fact, you know, the team has went out to I-Core at Stanford, and they gave us a lot of good industries to focus on. We realized that the estimation market might even, the consumer market might even be bigger, a lot bigger than the roofing market itself. So, Habib, do you have anything to add?
No, I think you covered all of them.
Okay.
Mm-hmm.
Thank you. Another question: have you considered using remote-controlled flying video cameras?
Yes, we've looked at that very much in depth. In fact, we've talked to several people that are willing to these quad rotor helicopters. We even have a customer that's going to loan us one. We're a little concerned about the FAA and how their rules restrict. You know, they came out no-fly zones for large buildings and so forth. But we think that as long as you stay below a minimum height, 300 feet, 1,000 feet, I can't remember the exact what they're coming out with, but bottom line is that you'll be able to use these, and some of the other people at Georgia Tech that we've worked with can actually let you map out the path that this quadcopter would have to take around the building, you know, to keep the distance the same, to basically vary the height to get the different roofing structures from different angles and so forth. We've looked at that. We've also looked at the concept of using an extended pole, either attached to a person or attached to, you know, a forklift, where they could, you know, basically get raised up and it could drive around the building structure.
Great, thank you. For those who want to get in touch with you directly, would you be willing to give out an email address or contact contact information that they can reach you at?
Sure. Do you want me to tell you over here, or do you want me to send it out to you, or what?
Yeah, I was going to say either put it on the slide so they can write it down right now, or just say what it is and they can jot it down.
Okay.
That would be great. Thank you. Okay, if anyone has any other questions, as I said, we are recording this and we'll be posting it at the fiatech.org website. I wanted to remind everyone that we also have our members meeting coming up October 15th, 16th, and 17th in San Diego. Registration is open on the fiatech.org website, so both Georgia Tech and Metalforming are members of Fiatech, and I know many of you are as well. So please take a look. The agenda, the draft agenda is posted, and we're filling that out daily. So we should have that confirmed in the next few weeks, and encourage all of you to come and you can talk to these folks directly as well. So thank you very much, Habib and William. We appreciate you taking the time. Like I said, we'll be putting a link on our website and sharing that with you. And if folks want to follow up directly, you've got the email there, bwilkins@metalforming-usa.com. So thanks again, and have a great day, everyone.
Okay. Bye-bye. Thank you.
Bye.
Bye-bye.
Thanks.